You know that old saying, a picture is worth 1,000 words? Well, it's a great line, but it also points to this huge challenge in technology. How do you actually teach a computer what those 1,000 words mean? Well, that's exactly what we're going to break down today.
Okay, so picture this. A beautiful photo of a sunset over the mountains. You and I, we see it and we instantly get the mood, right? The warmth, the feeling of scale. But a computer, it just sees a bunch of data, ones and zeros. So how on earth do we bridge that gap? How do we get a machine to understand not just the pixels, but the vibe behind them?
All right, so before we can get to the really cool solution, we have to talk about the problem. For decades, computers have stored information in these neat, tidy little boxes. But the thing is, those boxes have always been incredibly limited.
So in a traditional database, our sunset photo would look something like this. You've got the raw image data, the actual file, some basic info like the date it was created, and maybe a few tags that a human had to type in manually, like sunset or orange.
And look, this is fine if all you want to do is search for every photo you've tagged with the word sunset. But what if you wanted to find pictures with a similar feeling? Or maybe other landscapes that have that same warm color palette, even if they aren't sunsets at all? Yeah, simple tags just can't do that. They don't get the nuance. And this huge disconnect, it actually has a name. It's called the semantic gap. It's this massive chasm between a computer's rigid, structured data and our very human way of understanding context and meaning. And this gap is precisely the problem that vector databases were invented to solve. So, how do we bridge the semantic gap? Well, we have to teach computers to think less like a spreadsheet and a whole lot more like a human brain. We need to get them to think in vectors. The secret sauce here is something called a vector embedding. Now, don't let the technical terms scare you off. At its heart, it's really just a long list of numbers. But it's a very special list. These numbers are a mathematical representation of what the data actually means. And here's the magic part. Things with similar meanings get similar numbers, so they end up grouped together in this gigantic virtual space.
And what's so incredible is just how flexible this whole idea is. We can create these vector embeddings for pretty much anything. I'm talking images, like our sunset photo, of course, but also entire articles, text documents, you name it. We can even do it for audio files, like music or somebody speaking.
Okay, I know this all sounds a little abstract, so let's make it real. Let's actually compare the vector embeddings for two different photos, side by side, to see how this works in practice. Here's a really simplified look at the vector for our original mountain sunset. Now, in the real world, these dimensions don't have nice, neat labels, but let's just pretend for a second. Let's say dimension 1 is elevation, and it scores a 0.91, which is really high. Dimension 2, urban elements, is way down at 0.15, and dimension 3, warm colors, is up there at 0.83. Okay, now look at this. It's a totally different picture, a sunset at the beach. Let's check out its vector. The elevation score? Super low now, just 0.12. Urban elements are even lower. But what about that third dimension, the warm colors? It's a 0.89. That is incredibly close to the mountain sunset's 0.83. Are you starting to see what's going on here? This is it. This is the whole trick. By just comparing these lists of numbers, the computer can now see that even though these photos are completely different when it comes to elevation, they are almost identical when it comes to warm colors. For the very first time, the machine can actually understand that two different pictures share the same vibe. So that obviously leads to a pretty big question, right? We get what these vectors do, but where in the world do they come from? I mean, somebody isn't just making these numbers up. Exactly. How do you take something as complex and beautiful as an image and somehow distill its entire essence down into a precise list of numbers? The answer is AI. Specifically, very specialized AI systems called embedding models. You can think of these as powerful neural networks that have been trained on just massive amounts of data for one single purpose, to find the hidden meanings in stuff and turn them into vectors. The way it works is in layers. So when you feed some data into the model, the first couple of layers spot the really simple stuff, like edges and colors in a photo or individual words in a sentence. But as that data travels deeper into the network, the model starts to recognize much more complex patterns, like entire objects or the contextual meaning of a whole paragraph. And then, pop, out the other side comes our rich, super meaningful vector. And this isn't a one-size-fits-all kind of thing. No way. This whole field is incredibly specialized.
You have models like Clip, which is famous for understanding images. You've got Glove for text. And you even have models like Wave2Vec that are built specifically to understand the patterns in audio. Okay, so we've figured out a way to turn all of our data into these meaningful vectors. Problem solved, right? Well, not quite. Now we have a brand new problem: scale. How do you search through millions or even billions of these things without waiting forever? I mean, seriously, think about it. If you have a database with over 100 million items, trying to compare your search to every single one of them would be painfully slow. We're talking minutes, not milliseconds. It just would never work for any app you'd actually want to use in real time. And this is where vector databases make a really, really clever move. They make a trade-off. Instead of an exact search that's 100% accurate but takes forever, they use what's called an approximate search. It finds the vectors that are very, very likely to be the best match. And by giving up just a tiny sliver of accuracy, they get a mind-boggling boost in speed. They pull this off with a process called vector indexing. The database uses these brilliant algorithms, they're called approximate nearest neighbor, or ANN algorithms, to basically pre-organize all the vectors. It's kind of like creating a super smart map of all your data before you even start searching. And to do this, they use some seriously advanced methods. You've got algorithms like HNSW, which builds these incredible multi-layered graphs. Think of them like expressways and local roads for your data. Then you have others, like IVF, that group similar vectors into clusters, so you only have to search in the right neighborhood. But at the end of the day, they are all designed for one thing and one thing only: blinding speed. So why does any of this matter? What's the big deal? Well, it's because this technology isn't just some weird theoretical concept. It is the fundamental engine that's powering the AI revolution that you see happening all around you every single day. And maybe the single most important application right now is something called Retrieval-Augmented Generation, or RAG for short. The easiest way to think about it is this: the vector database acts as a perfect, searchable, long-term memory for an AI. So when you ask a large language model a question, it doesn't just make up an answer. First, it queries the vector database to find the most relevant factual information. Then it uses that knowledge to generate an answer that isn't just well-written, but is actually accurate and grounded in real data. When you boil it all down, that's what a vector database really is. It's a scalable, searchable memory for AI. It's the key that unlocks the ability for machines to truly understand and recall these vast amounts of human knowledge. So the question we're all left with is this: what happens next when AI can understand and remember not just a few books, but everything?